In this video, we're going to talk about the analysis of graphs, specifically with functions, and we're going to go over a lot of very important concepts for Algebra 2 and higher level classes. So it might be a good idea if you pause and write down the definition and the way to do this mathematically. The blue is the definition, the green on this page of notes is the mathematical process to find these items. So the first one is the rate of change, which is a ratio of a change in one variable relative to a corresponding change in another. In Algebra 1 and geometry, you knew this as slope. It was the change of output values divided by the change of input values. Maybe you knew it as y2 minus y1 over x2 minus x1. But in Algebra 2 and above, we use the terminology f of b minus f of a over b minus a being the first thing in the alphabet, b being the second, so you can see how that came about. So let's draw a visual since the focus of this lesson is on graphs. And if I were to draw a curve, I don't want to draw a line because in a line, the average rate of change is in fact the slope. But in a curve like this, you can see that the rate of change is actually changing all over the graph. It's actually positive here or negative there and then positive there. So it's important to understand that that rate of change can be found as an average by doing this. And the way that this works is if you chose a point here and you chose just, I don't know, a point here, the first point, because we go from left to right, would be labeled A as its input, and its output would be f of A, meaning the output with respect to A. And the second point, alphabetically, would be B, and that would be the function f with respect to B, the output of f with respect to B, and that would be our second point. So what you would do is you would find the value of f of B, it's just a point, you would label it and you would write it down, and you would put that value here, and the value of this point, its output would go there, you would subtract them, and then you would subtract the input B minus this input A, and you would find that value. Okay, so the next important concept for graphs of in Algebra 2 and upper level classes is the idea of an X-intercept. And an X-intercept is a point where the graph crosses or touches the x-axis. It's very easy to find. There's three of them in this graph. There's one here, and there's one here. And so a graph can have many x-intercepts, but a y-intercept is a point where the graph touches or crosses the y-axis. That would be here. And for a function, there's only one of these on each graph. It's only one that could be possible. So one thing that's important to understand is that a y-intercept and an x-intercept, you could actually in fact have the same number. So you have to label them correctly so people know what they are. So imagine that this y-intercept was at 3 and this x-intercept was at 3. I would label the x-intercept 3, 0, but the y-intercept would be labeled 0, 3. Otherwise, I would think they were the same thing, and it's the notation as a point is very critical for x and y-intercepts. So mathematically, the way you find an x-intercept is you substitute y equals 0 into a function and solve for x. Basically, what that looks like is that will look like this. You'll have f of x is equal to 0, and you will solve that for x. And in a nutshell, that's something you have to do multiple times in Algebra 2, depending on the chapter and depending on the function. The y-intercept, it says substitute 0 in for x equals 0 into the function, and then simplify using Gelndas. Well, that's just simply f of 0. So that's a whole lot easier. That just means plug 0 into the function and reduce it, which is a much easier process than the x-intercept, which involves solving. So the y-intercept is an easier concept to find. A lot of kids start with that when they have to do quizzes or assessments of any kind. All right, so the domain is all the input values of a relation or function. You find that by simply looking at the graph from left to right. So you basically analyze the graph. You start on the left, you go to the right, and you say where it exists. So you analyze the graph from left to right and list those input values in ascending order using interval notation. If it's a list of points, you use curly brackets. But if it has, if you have an endpoint that is open, you would use parentheses or closed. Remember, open circles are parentheses and closed circles are square brackets. Range is the same concept, but you're talking about output values. So the range is all the output values of a relation or function. That way, you would scan the graph going upward like this. So you start at the bottom, and you go to the top. You analyze the graph from bottom to top, and you list the output values in ascending order. Same idea with the notation. So after that, we have a maximum and a minimum. So a maximum is a point at which an increasing interval changes to a decreasing interval. Maximums are points. They're xy coordinates. A minimum is a point at which a decreasing interval changes to an increasing interval, and that is, again, a point. So let's go back and look at that graph that I was showing you so we can find them. So if I was looking at this graph, this right here is a maximum because, as you can see, the graph is going up, right? It's tending upwards, and then it tends downwards. So that makes that a maximum. And here it's tending downwards and then switches and tends upwards. So that is a minimum. There's actually a better way. So that's a maximum. That's a minimum. There's a better way to describe minimum and this tending word too that I was using. So I was saying tending up and tending down, and those are called increasing and decreasing intervals. So an increasing interval is as a function's values increase. So as I increase my x values, the corresponding y values also increase, meaning they go up. This is another way of saying it's the domain of the function where the rate of change is positive. So the way you do this is you simply state the domain of the graph where the graph is tending upward. So if I go back and look at that example, I would simply state this domain, and then I would state this domain because those are tending upwards. They have a positive rate of change. All right, so for a decreasing interval is as a function's x values increase. So as my x values increase, the corresponding y values decrease. It's the domain of the function where the rate of change is negative. So the way you do this is you state the domain of the graph where it is tending downward, and you write those. By the way, both these are written in terms of x. So again, I did say that was the domain. So domain is written in terms of x values. Here again, we're looking at the domain, and we would write the answer in terms of x's. So when I go back up and look at this example, the decrease interval is here, so you would just state this domain of the function where it's going downward. If you were walking, you'd be walking downhill here.
So looking at our first example, we're just going to analyze one graph at a time. And so when you look at this graph, the first thing you want to do is you want to label pertinent points. I have endpoints here. One's open, one's closed. I have a maximum, relative minimum. So the first thing I'm going to want to do is I'm going to want to label these points. And so by doing that, we've established where they are. Notice that some of the points are nice and even numbers, like that point is 1, 2, and this point is 4, -3. But I want to look at this minimum. This minimum may be at -1, but it's only about halfway through. So I would just estimate maybe a tenth here. That's going to be -1.5 or 0.5. And this point over here, I'm estimating it to be -4.4 and then +4.2 for the output value. So make sure you have organized that before you start trying to answer the questions that are presented. So let's take a look at the first question. Using interval notation, state the domain and range of the graph. So to do this, and it's important to understand that you need to scan the graph going left to right. So if I scan the graph going this way, right, the graph starts at this point, it keeps going, keep going, and it would end here. So I just use those input values. I would use this input value and then this input value because the domain is input values. So the domain would be the numbers -4.4 and then comma 4. And then to use interval notation, since this is an open circle, I use a parentheses, and since this is a closed circle, I use a bracket. Everything is a bracket unless you see an open circle, and then it is a parentheses. So to do the range, what we're going to do is we're going to go from the bottom to the top. And so we will start here, but the range value is going to use the output value. So it'd start here, it'd keep going. Remember, we're going all the way through. It keeps going until we get to there. So the range value would be -3. Remember, ascending order, so that negative has to be first. And then it's going to stop at 4.2. And again, same idea here. the -3 is a solid dot, so it gets a bracket, where the 4.2 is an open circle, so it will get a parentheses. All right, make sure those parentheses look nice and parenthesis-like. If you need to erase one and make sure you don't get them confused, make sure you take the time to do that so you understand the difference. All right, so now we're going to list the intervals or the domains where f is increasing and where f is decreasing. So if I take a look at what's happening here, I like to use red for decreasing. The graph is decreasing, meaning if I were standing here, I would have to walk downward until I get to this point, which is the minimum, which we can actually go ahead and label in these other points in a minute. We've already labeled it as -1, 0.5. I also have decreasing intervals here because I would have to walk from left to right. Remember, I have to go left to right. So I would be walking down here as well. But in between here and here, I would walk upwards. Okay? So if I were to list the increasing interval is the domain of this little piece here. So that would be from -1 to 1. And when you list increasing and decreasing intervals, you always use a parentheses because you can't include those points. Now the reason is, okay, and this might look like a point to you, but in upper level math classes, this is read from -1 to 1, which is what we see here. The reason I can't use a bracket on this point is I'm about to then use it in the decreasing interval. So for the decreasing interval, what I'm going to do is I'm going to start my decreasing interval here at -4.4, and it's also going to include this point because it's going from here to here and then stopping right there at -1. So the problem is, okay, is that you cannot include this shared point right here at -1 because it's both here and here, so it needs a parentheses. Now this needs a parentheses for a different reason. It needs a parentheses because it is, in fact, an open circle. Okay, so now let's look at this last interval. Ask yourself, it starts at 1, it goes to 4. Is the 1 shared? Yep, it's right there. So I have to use a parentheses, but now ask yourself this very important question. Is that 4 shared? It is not. It also has a solid dot. So that will be an inclusive point because it's not shared between an increasing and decreasing interval. All right, so let's take a look at our mins and maxes. Some of them are labeled, and some of them we have to sort of understand exactly where they are. So the first ones that are probably the most obvious to label are the ones that are here. That is clearly a minimum or a dip, and this is a maximum or a peak. So that is my local, right? Those are local. So I'm going to go ahead and say my local or relative, however you want to say it. We'll say local. My local min and local max. Now here's the thing about them, okay? There actually are more than just those two, and I'll explain why in just a second. So local min is -1, 0.5, and my local max is the point 1, 2. Now, where are the other ones? Well, believe it or not, this is a local max. The reason it's a local max is because I want you to think about if you were starting on a hike and this represented a hike. Wouldn't this be the highest point you were at? But the problem is, so that's a maximum, but the problem is it's not actually there because it's open. So since we can never decide exactly where this point is, we actually, even though it is a maximum, I can't include it in the maximum list. It would actually technically be undefined, which is really important for the global maximum. So when I look at the global maximum here, I would actually have to say that it is undefined. Undefined means basically open circle. So why is that happening? Well, we have to describe what's happened. We have to describe what we see in the graph. The graph is representing a maximum here, but I don't know where it is because it's open, meaning is it at -4.4 or is it at -4.39 or is it at -4.3999? We can never agree on it. However, we do know that it's there. So we don't list it in our local maximum, but we do say that our global maximum is undefined. Okay, let's take a look at the local minimum. We have a minimum here, and this is also a local minimum. Think about being on a hike. You would start, you'd go up, you'd go down, and you would stop right here. But that point is defined, so I can actually put it in my list for -3. And for my global or absolute, doesn't matter, those words are interchangeable. For my global minimum value, I'm going to list that point. So what is the difference between global and relative minimums and maximums? Relative or local are the list of everything you see. However, global max and global min, there's only one of those. There's only one tallest mountain in the world. There's only one lowest point in the world. There's one richest person in the world, right? So the global minimum or maximum, there's only one thing that'll be here. But over here, there could be a lot of them. It just depends on what your graph is doing. All right, let's take a look at some actual calculations. So this is where I'm going to start translating what these are saying, because they're not super obvious for students when they first start out. When you look at this question, it says find f of -6. What this is asking you to do, it's saying what is the output value of f at each of these input values. So the best way to understand this question is to simply label these points. So if I were to go and find -6, which actually isn't here. So the first point we have is undefined. So f of -6 is undefined because the graph only has a domain of -4. Okay, so that's undefined. Another way to shortcut that, if you don't want to say is undefined, is you could say does not exist, otherwise known as D and E. It's one of the only math shortcuts that's allowed to be used. So f of -6 does not exist. So f of -1 is right here. That's that point. And so what is the output value of -1? It's 0.5. So the way you would write that is f of -1 is equal to 0.5. And that is the answer. The answer is that. So what is f of 3? Let's take a look. F of 3 is here, and so this one we actually have to maybe kind of estimate where that output is. So I have a 3, and my estimated output would maybe be -1.5. You know, your teacher would probably be okay if it were off by a tenth, either below or above that number. So f of 3 would be equal to -1.5. And then again, if I look at f of 9, well, the domain only goes to 4, so f of 9 also does not exist. And so does not exist is not something we need to be scared about when we think about algebra or think about analysis of graphs. It's just something that happens when something is asked that is not in the domain of a function. All right, let's see if we can remember what this is asking. So it says, where is f of x equal to 0? Again, it's saying in English, what is the input value of f that has an output value of 0? And one way to think about that would be to draw a line at 0, but that's actually asking for the x-intercept, right? Because right here is 0, so it's actually asking for this point right here. So keep in mind, it really is helpful if you learn what these things are saying. Like this is the x-intercept. And then when you think about the next question, notice I just kind of changed it to try to remind you that this one is asking for the y-intercept. So it's important to know what these are saying because they come up a lot in Algebra 2. So the x-intercept would be written as a point, and that point would be, I don't know, it's a little bit past 2. So why don't we say 2.2? Again, if you were off by a tenth, your teacher would be fine with that. You could also say x equals 2.2 because it does ask for the input value. Both these would be acceptable, but maybe keep with the fact that it's the x-intercept. The y-intercept is right here, so that's right at that point, and that point is 0, 1. Another way to say that, if you were to see that, would be f of 0 equals 1, meaning I inputted 0 and I outputted 1. All right, so let's keep on this concept and look at a couple other ideas. So looking at this graph, when I look at these problems are asking me, where does f of x equal 3? That's asking me, where is the value of the graph equal to y equals 3? So that's basically, instead of saying 3, it's really saying, where does f of x, the graph, equal the line y equals 3. So if I take a line and I put it up at y equals 3 right here, it becomes pretty easy to understand what's happening, right? Because when I look right there at that line, so the graph f of x, the black graph, is equal to 3, the orange line, right there at that intersection. So once I see that and understand what it's actually asking, I can clearly see the answer. And again, labeling is just so important. And so what is the x value of that point? Let's see, negative 3.5. So the way I would say that is x equals negative 3.5. And again, if I were to label that point would be negative 3.5 comma 3, again, yielding that concept that it wants me to look at 3. So this next one says, where is f of x less than 3? So that's actually asking, where is it below 3? So that's asking for a domain, because it's below 3 this entire time here. The whole domain after the point negative 3.5. So negative 3.5 is where it begins to be below 3, and it stops being below 3 at 4 when the domain ends right here. And since this does not have an equal sign, I would use parentheses the whole time. If it did have an equal sign like that, that would make these brackets. So just keep that in mind, that some things in math are very subtle, and one of the most important, people will ask me all the time, why do I need to learn math? It really makes you pay attention very closely to details. I mean, think about that. Without an equal sign, I have to use parentheses, regardless of what the graph is saying. But with an equal sign, I'd have to use brackets. So just keep that in mind. It can be very, very subtle. All right, so the last one is the average rate of change. And the average rate of change is, again, it's a series of points, just like you had in Algebra 1, okay? So you just got to remember that it is, in fact, the slope. So to find this, what we're going to do is we're just going to label the points that they're asking us to find. So let's go, remember, this would be A. This is not a point. This is in a bracket. So this is an interval, and this would be B. So I'm going to go to negative 1, and I'm going to label that. Okay, thank goodness it's already labeled for me. So this would be A, and this would be f of A. So I already know those two things. They're right there on the graph for me. And then B, also labeled. First time you saw this in the graph, I wanted to have them nice and cleanly labeled. All right, so what I do now is I write down the formula and I simply substitute these numbers into that formula. So the formula is f of b minus f of a over b minus a. And again, I'm just going to go back to my graph. Okay, so f of b is 2 and f of a is 0.5. So 2 minus 0.5, we can go ahead and figure that out if we want. So 0 minus 2.5 is 1.5. All right, and then the input value B was 1 and the output value of A was negative 1. So it'll be 1 minus from the formula negative 1 because A was negative 1. That will come out to a positive, and so the denominator comes out to 2. And if you were to grab a calculator and take 1.5 and divide by 2, you would get 0.75 or 3/4. Either answer would be acceptable since it is a terminating decimal. Keep in mind that repeating decimals really, I don't know, it's probably a good idea. Fractions are never wrong, so it might be a good idea to say the answer is 3/4. So what that's saying is that between negative 1 and 1, the rate of change here, even though it kind of is curvy, the average rate of change on this interval is 3/4, or up 3 over 4.
In this example, we're going to do an analysis of a graph of two different functions, compare them, and also look at their input and output values. Keep in mind in this graph, the red graph is f of x, the blue graph is g of x. So when it asks you to evaluate or when it asks you to solve, it's really important to pay very close attention to what they're asking and what they give you. So in this problem, notice that they've given us an input value. So that means they're looking for an output value. And the best way to do this, the best way to do any problem with the graph is to label points. So if I go to 1 and I label this point at 1, I can clearly see that the input value is 1 and the output value is 2. So what is f of 1? F of 1 produces the value 2 on the graph. So same thing here for G. I just switch to the blue graph. I go to 1. I go down to the graph. I place a point, and I label the point 1, comma, negative 2, because it's at negative 2. So G of 1, input 1, output negative 2. So the reason that this is important is because all kinds of things can be asked you to do with these kind of values. So notice in the second problem, I'm asking you to find f of 1 plus the absolute value of g of 1. And even if I didn't have number 1, if number 1 wasn't here, I would actually start number 2 the same way by labeling the points. So f of 1 is 2, and g of 1 is negative 2. And I'm just going to follow GELMDAS. I'm going to drop down the unused items first. And the reason we found f of 1 and g of 1 first is because that was substitution, which is in the first step of grouping symbol, because the grouping symbol is this parentheses, and that parentheses means substitution. Then I will move to this grouping symbol, because notice it's on the outside. The absolute value of negative 2 is 2. Drop everything down, and then evaluate this addition. So the overall result is 4. So I could say that was 4, or I could say f of 1 plus the absolute value of g of 1 is equal to 4. And it makes sense graphically as well, because if you remember, the absolute value is distance from 0, and this distance right here from 0 is 2, and so is this distance, so the total distance is 4. So in this question, it asks, where is f of x equal to g of x? And I like to give little hints to explain what that means in just normal language. So where do f and g intersect is what that's asking, and they intersect right here at this point. So again, labeling this point is the key to understanding how to get the correct answer. Notice in this problem, they're asking for x, because x isn't given. Here, they gave you the input value, so you're trying to give them the output value. But here, they want to know, what is this input value? And the input value of that point is 2. It is the x-intercept, and if you want to actually give 2, 0 as the answer, that also would be correct. But since this is an equation, you probably want to answer it with x equals. So in the next example, we have where does f of x equal 0? Again, notice it doesn't give me the x, so it gives me what it equals. It's giving me the output. It wants me to find an x equals. And also remember from our definitions that when I set a function equal to 0, that's asking for the x-intercept, which again is actually at this point. So the answer would be x equals 2, or we could say 2, 0. All right, let's take a look at what happens when we have a composite. I don't want you to be afraid of composites. I want you to calmly go through it using GELMDAS. So what is this asking me to do? It's asking me, what is the output value of g of x after substituting in the output value of f of 1? So I got to go back to f of 1, the same point we've been looking at. The output value is 2. So f of 1 is 2. And then I just drop down, like any other GELMDAS problem, I drop down the pieces I haven't used yet. And now this is asking me to find what g of 2 is, which g of 2 is this point right there. Again, it's this value. So it's outputting or inputting 2 and outputting 0. And I could have also said g of f of 1 is equal to 0. And I wanted you to see that because notice I've used this point to answer 3 questions. But in this problem, I'm answering with an x value, right? Because it doesn't give me the x value. But in this problem, they put an x value in the problem, so I'm answering with a y value. It's important to understand inputs versus outputs and what's given and asked. All right, we'll move away from that point now and look at a different one. So this one's asking for f of 0, meaning what is the output value of f of x after substituting in the output value of f of 0? So let's start by finding the inside of our grouping symbol and find f of 0. If you remember from your notes, f of 0 is the y-intercept. So I input 0, and it's outputting 3. So I'm just going to drop down that f of 0 is equal to 3, and everything else will just be rewritten for the next step of the problem. So now the problem, it goes from f of 0 to f of 3. I go to 3, I find f's value. F of 3 is outputting negative 2. So f of 3 is negative 2, or I could say f of 0 is equal to negative 2. Okay, so now we're going to switch over to looking at increasing and decreasing intervals. Keep in mind that the definitions for those are simply where is the graph tending upwards or where is the graph tending downwards. Another way of thinking about it is where is the rate of change positive, and we're looking specifically at f of x. I like to use arrows because you can clearly see those arrows are pointing upwards, and it wants this domain. It wants the domain from this point, so helpful to label it. That point is negative 2, comma 1. It wants the domain, so negative 2 until that point right there, which is 0. So the increasing interval will go from negative 2 to 0. Now, what should we use? Should we use parentheses or brackets? Well, this one's pretty obvious. Open circles are parentheses always. But this point is shared because what's going to happen right after this point, it starts to tend downwards. It has a negative rate of change. So this negative rate of change is indicating a decreasing interval. Okay, and that decreasing interval starts at 0, right here at the same point. It's shared. So because this point is shared, I use a parentheses because it can't be both increasing and decreasing at the same time. So just keep that in mind when you do that you're careful with using parentheses on shared points because they can't be two different things on the same interval. I can't put a bracket because that would mean they're both increasing and decreasing. So as we go down this interval, we realize, oh, we're going down and we come to this arrow. And it's tempting for students to say that's negative infinity. You can actually label arrows as well. This arrow in the x direction is going to positive infinity, but in the y direction or the output direction is going to negative infinity. And since we answer decreasing intervals with x, it's actually not going to negative infinity, it's actually going to infinity because it's the domain where this graph is tending downward. All right, let's take a look at local and absolute minimum and maximum values. So remember, local could also be said relative and absolute could also be said global. So if I look at my local let's start with local mins. If I look at my local min, this graph, I picked it because of the fact that the local min, it's very interesting what's going on, because if I look at the graph carefully, I realize there isn't a local min. I mean, there is a min here, but that's an open circle, an undefined point. That does not exist. And then if I go around, I do have a maximum right there, so I can write that down if I want as my local maximum, 0, 3. But the local minimum, it goes to negative infinity. So what I have to do there is I have to realize, okay, well, that does not exist. So I can just use that abbreviation, does not exist. Some students would say negative infinity, but negative infinity is not a number that we can actually hammer down and put our finger on. So it's probably better to say does not exist. So when I do the absolute absolute minimum, it also doesn't exist. It would be probably more appropriate to put that infinity sign for the absolute minimum. But again, probably the best answer at this point is does not exist. That's actually taken care of later in Algebra 2 by a concept called in behavior. That's when we would really be using that negative infinity sign. So for now, we'll say does not exist when we see infinity. In the local maximum, since there's only one max, my local maximum is going to be only that one that I have. The only maximum on this entire graph of f of x is 0, 3. All right, so let's go back and look at the concept of rate of change. So we're switching over to the blue graph. So what we're going to do is we're now going to find the rate of change of the blue graph, g of x, from negative 1. So let's label that point at negative 1. G of x is equal to negative 2. And at 2, we're back to this point that we've used before, which is the point 2, comma 0. Now, I want you to understand this looks like a point, but do you see how there are square brackets? And I even use the word over. This is the interval, negative 1 to 2. So the formula for average rate of change is f of b, meaning the second value that you see for output, minus f of a over b minus a. So if I go back and take those points that I wrote down initially at negative 1 and label them a and f of a, and then b, and then f of b, this becomes a very simple subtraction problem. It's labeled, it's clear to understand. F of b is 0, a subtraction from the formula. F of a is -2, so I have two subtractions. That will become addition. B is 2. I have a subtraction from the formula, and then a is -1, so another subtraction sign. So this will be addition, and this will be addition. So the rate of change comes out to 0 plus 2, which is 2, and 2 plus 1, which is 3. And this is a perfect example to give you a nice visual of what rate of change is. Since this is linear, this doesn't make sense on a curved graph. That's why I picked g of x. You can clearly see that we went up 2 and over 3 to get to that value. So the rate of change here, my slope here is 0. My rate of change here is a positive number, but the average from here to here is 2/3. And maybe that makes it a little bit more visual sense. All right, let's take a look at some inequality problems. So this question is asking, where is g of x less than or equal to -1? Which means, in just regular language, where is g below or touching the line y equals 1? So again, it really helps to label. First thing we need to label and understand is that when it says g is less than 1, it means g is less than y equals -1, which, if you recall from Algebra 1, is a horizontal line. So I'm just going to take a horizontal line, and I'm going to put it right here on the graph, and I'll even label it for you, y equals -1. And what I'm trying to find here is I'm trying to find the intersection first of g and this value. So the intersection's right here at this point. Again, going back to labeling, that is 1.5, comma, output should be -1 because it's intersecting there. So where is g below this? G is below it all right here. So I want to give the domain from left to right. That point right there, we haven't labeled it, so let's do that. That point is -2, -2. Okay, so to find the domain, I'm going to go from -2 to 1.5. And then I'm going to be careful about my interval notation by looking at the question. So the question has an equal sign. An equal sign means bracket. It means include. So I have a solid dot. It makes sense that that's a bracket. I have an intersection here with an equal sign, so that's a bracket. Keep in mind, if this was not here, these would both be parentheses, which is in fact in the next example. Okay, so looking at number 8 here, we have to be careful that we understand that this one does not have an equal sign. So that's going to change how we write the answer. So let's first understand what it says. Where is f of x greater than 2? Meaning, where is the graph of f above the line y equals 2? Remember, anytime there's a number being compared to a function, you can write that number as a function, in this case, a horizontal line. So if I'm going to clean this up a little bit. It's gotten a little bit busy up here. So if I take a look at this graph and I put the horizontal line on 2 right here, I'll even label it as y equals 2. Okay, what ends up happening is that produces two intersections. They're pretty clear to see. And I want to label those. Again, labeling is so important. So if I label this point right here, we get -1 point, maybe 2 approximately, within a tenth. That'll be fine. And then the output value is 2 because we're intersecting the line y equals 2. This one's a little clearer. This point is clearly 1, 2. And since I'm looking for the x, the domain of where f is above, right? F is above this line right here. I'm looking for this domain, which would be here and here. So f is greater than 2, above 2 on this interval here that I'm coloring in. So I'm going to go from -1.2 to 1, -1.2 to 1. Now be careful with how I do the next part. Some students will get lulled into thinking, oh, I just got to use brackets. But this problem, it's not equals. And in fact, it's more accurate to say this is an open circle question. So these dots that we colored in, they're more like open circles here because I don't have an equal sign of the problem. So these should be parentheses. And that is the interval. The interval from -1 to 1 is where f is greater than the line y equals 2. The last question is asking, well, where is the graph f of x above g of x? So where is f of x greater than or equal to, so this is going to use brackets, or equal to g of x. So that happens if you look at the graph, f of x is above g of x this whole entire time right here. That whole time, until we get to this intersection that we've used many times in this lesson, until we get to 2, we have a graph where f is greater than g. So what I want to look at is, again, I want to label this point. This point is -2, 1. Let's decide on the domain. Let's agree on the domain. So f is greater than g from -2 until 2. So we'll write that down, -2 to 2. And you would think that we would use brackets. And I'm going to go ahead and put brackets because it has an equal sign. I want you to look carefully at what's happening. It doesn't make sense to have a bracket here because that point doesn't exist. So you have to be very careful that even though the question says use brackets, the actual problem says I don't exist at this point, so I have to use a parentheses. And then I can use a bracket here because that point does exist. There is an intersection. It does exist, so I use a bracket. So I hope this video has been very helpful to you. You might want to watch this part of it again. There's a lot of information here, a lot. And one of the things you have to understand about math is it is a language. It's a language that is universal to all speakers of other languages. And so these notations, these parentheses, these brackets, the analysis, the g of f of 1, it's all universal. And the precision of how we grammatically use the language of math is the key, actually, to success to all classes from Algebra 2 and beyond, all the way into college, into calculus, and even into science classes like physics. These notational nuances are critical.